Okay, so hello everyone. I'm Berard, and I'm an undergraduate student in Dr. Sabrina Leslie's biophysics lab at McGill. So we're a new lab that started in January, and my goal since then has been to design and construct a new single molecule imaging device and perform some experiments in DNA confinement studies. So we've collaborated with another professor at McGill, Dr. Walter Reisner, to combine the click imaging technology, which I'll talk a bit more about later, but Chris did the first presentation on that at the beginning. So we've combined that imaging technology with glass substrates containing etched nanochannels in order to trap and align DNA in these nanochannels. So there are several reasons for wanting to study the confinement physics of DNA. First of all, the physics of confinement of DNA below the coil size of the polymer is not very well understood. So there's a lot of new physics to be studied there. Also, there are many potential applications to biology, such as in sequencing. So today's sequencing techniques have a few key drawbacks, such as they require a lot of fragmentation of the DNA and amplification to produce relatively large sample volumes. So now, when DNA is confined into a nanochannel, so DNA has some property called the persistence length. Persistence length is a measure of the stiffness of the DNA. So for DNA, it turns out to be 50 nanometers, and it's the length at which DNA behaves like a rigid rod rather than like a soft flexible glue. So at 50 nanometers, the DNA can be considered to be stiff. So if you insert, right here's the DNA into a nanochannel of width larger than the persistent length, then the DNA has room to bend around in the channel, and it sort of forms these blobs. And what we want to do, though, is extend the DNA fully so that we can look at it under a microscope. So we need to use a channel thinner than the persistence length, in which case the DNA can only bend off the walls because deflect off the walls because it's too stiff to sort of bend around in the channel. All right. So some previous techniques that have been developed to do this involve using either very high pressures or electric fields to flow the DNA horizontally through these nanochannels. Be something like this. So you put DNA in these reservoirs, apply a pressure there, and flow them here horizontally through the channels. But the problem with this is if you want to use channels that are below the persistence length of 50 nanometers, it's going to have a very high resistance to flow. And also, the DNA are relatively unconfined over here. And there's a large free energy barrier to push them into these tiny channels where they go into such a low entropy state. Now, just a quick review of CLIC. So CLIC is convex lens induced confinement microscopy, where we inject a sample between two glass cover slips, and that are separated by about 35 microns. And if you just look at that in the microscope,